Hi, this is Ms. Oberly, and I'm back with lesson 02, real numbers. Your job by the end of this lesson is to classify and use real numbers. And you should remember from the first video that you watched that real numbers can be classified in two categories. They're either rational or irrational. And rational numbers can be classified as integers, and some integers are also whole numbers, and some whole numbers are also natural numbers. Oops. Here's our first example. Example 1. We're going to classify the following real numbers. And remember from our last video that rational numbers can be written as a fraction. And sometimes that fraction, we could use our calculator to find that estimate as a decimal. I'm going to calculate this one really quickly. And when those decimals end up being a repeating decimal, those are also rational. So when we have an integer over an integer, that's a rational number. Part B, square root of 81. You should recognize this as a perfect square. The square root of 81 is also known as, what times what is 81? It is 9. So since that equals 9, we know 9 is both a natural number, because it's a positive counting number. It's a whole number because whole numbers just add on 0, so it can also be classified as a whole number, or it could be classified as an integer, which means that it is also rational. And part C, the square root of 56. Now, is this one a perfect square? Will we get a whole number out or a natural number out when we take the square root of 56? And the answer is no. When you take the square root of 56, you end up with 7.483. And if I'm looking at my calculator, I'm not noticing a pattern. It goes on and on forever. So this is not a repeating or terminating decimal, which makes this number irrational. Alright, and for example 2, we're asked to graph each set of numbers. We have some set notation in part A. And looking at the set of numbers, I determined since the denominator of all of these fractions is 3, it would be best to count by thirds. I wanted to make sure I included all of the numbers in the set, and now I can go in and plot this finite set, which just means it has an exact number of solutions, which are just points on the number line. Alright, for example B, this is read as x is greater than -2. And if x is not in that left-hand position, I always like to rewrite the inequality with the x first, because there's a little trick you can use if x is first. Recall from last year that greater than does not equal -2, and since it does not equal, we're going to have an open circle. Oops, sorry about that call. It's my husband wondering why I'm still at school. So I'm putting an open circle at -2, and then I'm following the arrow. I'll grab another color so you can see what I mean by that. So the arrow is pointing in this direction. I know I'm going to have an arrow pointing in this direction. And the solution here is every number greater than -2. For C, B is less than or equal to 4.5. So I have to locate 4.5 on my graph. This less than or equal to inequality tells me that it's a closed circle. And again, I'm following the arrow. So the solution is all of the numbers that are less than or equal to 4.5. Alright, thinking back to those perfect squares from the last example, I want to think about the perfect squares that are closest to a square root that is not a perfect square. So I listed them before. Square root of 4 is 2, square root of 9, square root of 16. Oh, check that out. 15 falls right in between the square root of 9 and the square root of 16. That will help us estimate the square root of 15. So if you like to visualize this, whoops, I turn it down quick. We know that the square root of 16 is 4, and the square root of 4 is 2. And in my head I'm thinking, man, the square root of 15 is a lot closer to the square root of 16 than it is the square root of 4. So the square root of 15 is between 2 and 4, a lot closer to 4 though. Well, and actually, I'm looking at this now and realizing I could get a lot closer than that because the square root of 9 we know is 3. I kind of left that out, which we talked about here. So really, I should say it's between 3 and 4, but still a lot closer to 4 than it is to 3. If you wanted to write that as an inequality, we could say that 3 is less than the square root of 15 is less than 4. We can do the same thing for 130. So we need to find some perfect squares that are around 130. We talked about 121, which we know is 11 in the last example. And we also know that 12 times 12 is 144. So the square root of 144 is also a perfect square. And check that out, 130 falls right in between there. 130 is a little bit closer to 121. So if we were going to graph this on a number line, it keeps acting up a little bit. If we were going to graph this on a number line, we know that this is between 11 and 12, but the square root of 130 is going to fall closer to 11. An inequality, again, it's between 11 and 12. It's greater than 11, it's less than 12. So 11 is less than the square root of 130 is less than 12. All right, let's see if you took out of this what you needed to. It's time to write your summary. Real numbers can be classified as either what or what. And then we broke down those rational numbers and talked about natural numbers. Give us a definition of what they are and an example. We then talked about whole numbers, give us a definition and an example, and integers, again, a quick definition and an example. Rational numbers are blank, and an example is blank. Irrational numbers are blank, and I should scroll down for you. An example is blank. Perfect squares are and can be used to blank. All right. Good luck, algebra students. Thanks for listening and taking